All right, welcome everyone. So today we're going to talk about chapter 7 of the Hamel book. So this is about ensemble learning, which allows us to talk about random forests. And then I really think gradient boosting is so important. It really should be in the title of the chapter, but it isn't. As always, I want to thank the folks at Aquillius for hosting us here. So if you're looking for co-working space, you can talk to the Aquillius folks. That's what they do for their regular day job. And then just a quick reminder that we're having our social on Friday, and then the next chapter, our monthly meeting a week from today, Saturday. So we have a cool talk lined up. Someone's going to talk about how he created a chatbot application, vibe coded. So, as someone who's not like a coder, doesn't know how to build apps. And then we'll have the usual, the monthly ML news, and a little bit of an update on computer vision. All right. So before we jump in on today's, as usual, what I'd like to do is see if there are particular questions that people have. If there's any concept from this that you want to hit on, I'll make a note in the notes, make sure to kind of hit that as we go. Otherwise, I'll add a little bit of commentary on a few of the sections, and then at the end, really kind of talk about in this chapter multiple times the author talks about bias and variance, but I find that those concepts are kind of unintuitive, and so hopefully can help understand this in a way that when you're actually dealing with some kind of ensembling or building a gradient boosting machine, that you understand the intuition of like what's going to help, what you're trying to do. All right, so any particular questions, topics before we get started? Ah, okay, I meant to do that, I forgot, sorry. Let me put that in the chat. All right, so then let's get started. um so this chapter has a few different topics in here. So it starts with simpler things, voting classifiers, then moves on to bagging and pasting, random forest, and two different kinds of boosting are covered in detail, the eta boost and the gradient boosting. And then it talks about stacking. So I wanted to highlight that this chapter doesn't really distinguish between the kinds of ensembles that you're sort of more manually putting together versus the ensembles that are like algorithms that are programmed in a library that just fundamentally use multiple training steps. And, um, if you're doing a Kaggle competition, you'll probably be doing a tiny bit of ensembling, but it is possible that you could work in the real world and not use an ensemble, like go at least a year or years. So we were talking about econometrics. There's plenty of times when in business, ensembles tend to be slower to train and more expensive. And so I think it's important to have this delineation between the principles are the same, so it's good to understand them, but manually doing an ensemble is something that does not come up very often, whereas using these algorithms like gradient boosting is the conventional wisdom, the most powerful, the most commonly used algorithm on tabular data. So um so a very, very stark difference. All right. So the first section was voting classifiers, starting us off easy. Basically, you train a bunch of different models and they just make their predictions like normal, and you're just combining the predictions in a number of ways. So if it's a classifier, um, then you can't really say it's like 3/4 dog and 1/4 cat if you have 3 votes dog and 1 vote cat. So usually you could just do something like majority vote. Okay. If you have probabilities, then what you can do is you can blend the probabilities. And what that then does is it weights the more confident different word I was looking for, the more confident ones. So imagine that, you have three models that say 50%, 49%, 51%. I think it's, a dog. That's not like terribly helpful. But if the last model says 99%, I think it's a dog. Okay. That would be a case where the soft voting using the probabilities is going to weight that 99 a lot more than any of the 50s or 51s, so to speak. Whereas hard voting, it would be like, nope, a 51 counts just as much as a 99. All right. So that's our step one. That's our voting classifiers. So then the next level of complexity that the author goes into is bagging and pasting. FYI, bagging is more common than pasting. I'm not sure if there's a lot of really good reasons. One thing I do know is that uh, there's a footnote. It says like the term bagging is actually a smushing of two words, bootstrap aggregating. And in statistics, this idea of the bootstrap is if you have n data points, then you take n samples at random with replacement. So you end up with an equal size data set, but some of them are going to be duplicates. On average, like 67% of them show up, and about a third of them don't show up at all. But a very interesting thing happens when you do bootstraps, which is that the statistics of the bootstrap have a tendency under a wide range of conditions to match the statistics of the original distribution. So this bootstrapping is a very powerful technique in order to get you some variety. But when you want variety, you don't want variety from a different distribution. I could give you variety just by using a random number generator. That's not useful. What you want is variety that actually helps you with your particular problem. And so I think that's one of the reasons why bagging is more common, because you're sampling with replacement. And the most common form of bagging is not, I pick some number of things that I'm going to sample, but I sample exactly the same number as data points that I originally had. So it is technically possible, if you're doing bagging, to say I have 5,000 data points and I'm going to do a bag of size 1,000. But by far, the most common thing is you do 5,000. And again, that's because all of that statistics research and literature is around that case where the sizes of the two are equal. I'm going to guess, I'm not a great statistician, that if you did slightly different sizes, if you did 4,000, 3,000 instead of 5,000, you're probably going to get very similar problems. You can easily imagine that in the extremes, if you went from 5,000 down to 100 data points, you can't necessarily expect the statistics to be the same. And by the same token, if you went from 5,000 to 5 million, then maybe because you have so many repeats, maybe certain things, variance or whatever, like starts to look different. So the safest thing is you stick with the same number. And so that's the default in these different algorithms if you look at them. So the bottom line is, now, instead of having to have just a bunch of completely different models that you came up with on your own, like, oh, I'll do one linear regression, I'll do one support vector, I'll do one whatever, and voting them. Now you could use the exact same algorithm. I could do 100 linear regressions, and they're just all going to be trained on different data sets, because these were all bootstrapped from my same training set, but ended up with slightly different examples. You could do 100 trees, you could do 100, whatever. I made a note here. We'll talk a little bit more about bias and variance at the end, but yeah, it gets discussed a lot, and I find the statistical ideas of bias and variance not to be terribly intuitive, except in the simplest extreme scenarios. So a linear regression requires your data be linear, and so that is a very high bias. And then everything else, it's like hard to compare, high or low bias or whatever. It's lower than linear regression. All right. And then the variance part also I find a little bit hard to think about. All right. Any questions about our bagging and pasting, or primarily bagging as a way of basically being able to have more models just because we have now more different training sets, even if we use the same algorithm? Oh, um, so in the future, if we use the mics, so the question is, what is pasting? So pasting is where you change the algorithm to do sampling without replacement. So you can do sampling less than n, and you can do sampling up to n, in which case you just wind up with your original data set. But you can never do sampling without replacement greater than. So you could never have a size 10,000 data set based on 5,000 data points. But with replacement, with bagging, you actually could do that. You would just have more duplicates. So you would have maybe, I don't know, I'm just going to guess 12% of the data that doesn't appear at all, a bunch of data that appears 3 times, some that appears 2 times, and whatever. And so I actually have never used pasting once ever. So, but it, I think part of the motivation, to be honest, is this is a book that's supposed to cover Scikit-Learn. So if Scikit-Learn offers it, then it's in the book, regardless of whether it's commonly used or not. Any other questions? Okay. Um, oh, yeah,
Thanks.
please.
Um, so where exactly in the pipeline of training a machine learning model would I want to bag or paste,
Great
or
question.
does it vary?
Great question. So, um, there's two answers to that question. So if you were manually doing bagging, okay, it would probably be at the point where you've already done some different modeling and stuff. So you've done your EDA, you've analyzed your data, you've done a little bit of modeling, and now you're trying to get squeeze a little bit more power out of a model, than just training it once. So if you're like, hey, I like this linear regression, but I think maybe it could be a tiny bit better, then you could do bagging and you could say, I'm going to train 100 linear regressions and average them together. Okay, that's one scenario where you're manually doing it. The more common scenario is bagging is fundamentally used in algorithms that we're going to cover later in the chapter. You don't have to do anything. You just load the library and you say train it. But under the hood, you can understand, this is what it's actually doing. Cool. Thanks for the question. All right. And so when we talk about regularization, one of the things we often talk about is, simpler structures in the real world seem to generalize better. Okay. And so if you look at this figure 7.5 that's in the book, when you train just one decision tree, you can see it has these skinny, pointy, they're rectangular, but they're these skinny, pointy structures in the shape of the yellow and the orange. Okay. And the thing is, it's pretty intuitive to me that if you average together the predictions of 100 decision trees, it would be very difficult for the average to have such skinny, pointy structures. And as you can see on the right, it does seem to be, a lot smoother. Okay. It's still got some jaggies along the decision boundary, but and so this is a good intuition in terms of why bagging helps you, is because if you're a little bit overfit in one area and you have 100 of them, hopefully the other 99 are not all also overfit in this one area. And so they'll kind of pull you back. And in the reverse, if you're a little bit underfit in this area, hopefully the other 99 on average won't all be underfit. And so then they'll pull you a little bit back. Um, I cannot think of an example where your data actually is uh, extremely pointy. But if you ever did run into some problem like this, so if I don't know, you were somehow growing crystals or whatever, and it's just like you make this tiny little change and all of a sudden it's a completely different shape and whatnot, then you might actually find that some of our standard regularization techniques don't work well because what they're trying to do is just sort of smooth things out. All right. Another important concept is this idea of out of bag evaluation. All right. So let's, for simplicity, use a much smaller number. Okay. Let's say I did bagging 3 times only. Okay. Not 100. So I have my data set, 5,000 data points. I do random sampling and I get 5,000 data points. But again, some of them are repeats. So there's about 3,500 unique data points. Some of them are doubled. And then there's, another like 1,500 or so that don't appear at all. Then I do this a second time. And once again, there's approximately whatever mid 3,000s unique data points and a slightly different 1,500. There may be some overlap, but a different 1,500 that don't appear. And I do that a third time. All right. What out of fold evaluation says is I'm training my model on the bagged data. And so that roughly 3,500 unique samples, but some of them are repeated. So it's still size 5,000. How can I validate the performance? Because my training performance could be highly overfit. My loss could be 0, hypothetically, on that. Well, what I can do is I can evaluate it on the 1,500 data points that were not used. It's not that I picked these 1,500, it's just that they randomly were not part of that bootstrap. Okay. Then when I want to evaluate the second one, I can't use that same 1,500. I have to use the different 1,500 that were not part of the second bootstrap. But if you keep track of which data points did get randomly sampled and which ones didn't, again, I'm saying the roughly 1,500 that didn't, then for every time you do a bootstrap, there will be approximately a third of the data that doesn't get used, and you can use that for validation. And so I put in my notes that if you think about this, then if you had 3 of these bootstraps, it's a lot like 3-fold, k-fold cross validation. The difference here is instead of evenly dividing the data in thirds, we're doing a bootstrap for training things, so there's some duplicates. But we still have this phenomenon where we have sort of about a third of the data that we're doing validation on and 2/3 of the data that we're doing training on. And again, it's the statistical properties of the bootstrap that having those extra duplicates actually gives you some benefits relative to if you just divided your data set into 2/3. So the key thing here is, again, thankfully, these libraries implement this. You don't have to keep track of it yourself. But when you see out of bag evaluation scores, it's evaluating your trained model on data that it has not seen. That's super important. And technically, it's evaluating each round of training that you do on a different set so that none of them are ever being evaluated on data that they saw, but it actually gives you a pretty good, pretty accurate form of validation. And so when we talk about these next algorithms, the random forest and the gradient boosting, you will see that they have this out of bag score. And what I'm trying to get at is you can trust that out of bag score, that you don't need to further add cross validation on top of a random forest. You can really trust the out of bag evaluation that comes with that out. So does that make sense? Any questions about what's the point of out of bag evaluation, and hopefully it's clear that out of bag is not cheating. You're not ever evaluating it on data that it's been trained on. And ultimately, if you do a lot of these, if you do 100 in your bagging, 100 different models, eventually every data point's going to be in the out of bag part for some of the models. And so on average, you'll see all of your data, just like in cross validation. On average, you'll see all of your data get used for validation and all of your data used for training, but never at the same time on the same model. All right. If there's no questions, then the last section here talks about random patches and random subspaces. I'm actually, to be honest, not familiar with this terminology, but I'm familiar with the concept. Okay. So if you can use subsets of your data, you could also use subsets of your features. All right. So if you were predicting housing prices and you had number of rooms, square footage, does it have a pool, how many bathrooms, and you had 30 of these features, if you wanted to add some randomness, you could train models on only 20 out of the 30 features, and you could randomly pick which 20 features each model gets. My intuition is that randomly sampling the data is sort of less detrimental than randomly subsetting the features, right? Like, for example, like my limited experience is that house prices are very correlated with the size of the house, the square footage. So if you left that one out of your 30, if you only kept 20 of them, that would be way more damaging than if you left out is the washer and dryer new or old, you know, or something like that. So if you're going to be implementing some form of random subsets of features, my intuition is you probably are going to want the number of models you train to be on the large-ish side. You're not going to do this with 3 models. Like 100 models, it feels like, okay, you're going to cover your bases a lot more safely because on average, maybe, 70 of those models included square footage. And so even though a few of them didn't, and they might be weaker models, they will in general tend to get outvoted by most of the models. You also wouldn't want to do something where the subset of features that you use is very small. So I said like 20 out of 30. I can't imagine where you train just 3 out of the 30 features and then repeat, right? That would be a extremely detrimental thing. But hopefully the intuition is the same though, that without you having to go and collect more data, you can train multiple models. You can train multiple models by having slightly different training data. You can train multiple models by having slightly different features. And this will give you a variety of models. And in some cases, probably many cases, doing this subset of features, you average the results, you'll get worse results than if you used all the features. But there's times when this might actually help regularize things if you have a model that's really just tending to overfit. So maybe in some instances, if you really don't have very much data, so if you only had prices on 200 houses, maybe this somehow would help you from otherwise terribly overfitting. Okay. Um, Again, you're not very often going to do any of this stuff, the bagging or this subset of features manually. But these are key concepts to understand because we're going to see them in our powerful algorithms. Any questions? Yeah, go ahead, Ron.
I think two things. So the out of bag evaluation can sometimes be a little bit confusing because that's actually like if you're doing the format that we've talked about before, where you're doing a train test split, your out of bag is your training set again, but you're making a bunch of train test splits on your training set. So you're measuring your performance on the training set, but it's valuation square again. And then you can have out of bag, and then you can also have out of fold on top of that. So there's two separate things going on. So you can get your out of bag performance, and then you can get your out of fold performance. And those are two different numbers, but typically you would expect them to be actually pretty similar. Your out of fold might actually show up higher because your out of bag is for the models all stacked up, and the out of fold is saying use all of them in combination. So you can end up in the kind of confusing position where your out of bag is worse than your out of fold. Um, the random patches, random feature stuff is very, very common in Light GBM and XGBoost. And it's actually, I would say, one of the critical features of it. So in the typical setup where you just say, I'm going to just subset my data over and over again and train it on random samples of my data, that's already becoming very robust because you're pulling in random data points. But then if you say, I'm grabbing random features, you end up with like 1,000 or 10,000 trees that are all trained on random subsets of the data, random subsets of the features. And that can end up being very, very robust because if you have one feature that's poison and sometimes it's included, sometimes it's not, then in aggregate, it will end up something very smart regardless. So it makes it so you really don't have to spend nearly as much time on the feature prep and is this feature good, is this feature bad. If you just say, okay, pull in 80% of the features most of the time, then you end up with something that's, even if you have a column that's just total poison or random noise or whatever, you end up with a model that pops out that's totally fine. So two points I wanted to say.
Yeah, thanks, Ryan. That's really good. And we'll get to those algorithms in just a second. And so if you have questions, I ask you to hold on one second. In the chat, there's a question: could random patches be used for feature engineering, like for selecting which features? I think the concept, sort of, but probably you wouldn't literally do this. So there for example, when people talk about regression, they do stepwise regression. You can do regression with different subsets of your features. And that is something that people do, but it wouldn't necessarily be part of this random patches algorithm. Okay. The other thing, which we'll get to, is when you train these powerful algorithms like random forest and gradient boosting, they're going to have this wonderful feature that they can output feature importance, which will tell us how often something was used in helping build the model. And so that actually is something that I've done, where if it's an environment where you're not going to use that model, you're going to end up using something else, this feature importance still tells you a lot about what data was helpful, was not helpful in terms of building the model. All right. So with all of that foreshadowing, let's actually talk about random forest, our first super powerful algorithm. Okay. Um, so in the random forest, basically, to put it simply, we talked about bagging. We're going to do bagging specifically with decision trees. Okay. Um, the other thing that the chapter explains is exactly what Ryan was talking about, is that it will use this random subset of features thing, but it's actually using it in a slightly different way, because the way trees are built, you start at the top and you keep splitting, 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 splitting as you go down. Okay. The random features is not fixed for the entire tree. The random features, the dice, the random number generator is re-rolled at every split. So what that means is that if you had a super important feature like square footage, it might be, if you have all the features, the very first split that you would do, because it's the most important thing. When you're building trees in this random forest with that turned on, then if it's not available in the first split, it still could be available further down at the next split or the split below that. So if something is super important, then odds are most of the time, depending on your tree depth, it's going to be available to you at some point. But what this does is it forces the trees to be built differently, because otherwise you might find I built 1,000 trees, but every single one of them square footage was the very first split. And so the whole point of this was to get different trees so that we can do some kind of voting and averaging. But if they're all very identical, then that's not really helping us. The point of this is we wanted different ones. This is a way to force the trees to not be too bad, but to be different. And it turns out that you can do this kind of handicapping, like tying one arm behind the back for these models, a lot. and still amazingly get pretty decent results. So I don't recommend you do this as your like go-to, but there's been research on if your trees are forced to be only depth one. So they get one split and that's it, nothing else. So they have a special name for this. They call these trees stumps. Okay. Because they have no branches. All right. It turns out that if you built a large random forest of just stumps, it would perform pretty well. Um, and that's maybe slightly unintuitive because these are really, really weak individual trees, really weak models. Okay. But yes, what Ryan mentioned is in fact one of the superpowers, and there's been a bunch of research. I haven't really read the details closely. I don't know exactly the math behind it, but the default, what's recommended, is the number of features you allow at any one given split is the square root of the number of total features you have. So if you have 25 features, you would allow 5 to be used randomly and omit 20. So it's actually pretty heavy, right? Before I was saying if you were just manually doing this, you probably don't want to eliminate too many features. Here, again, assuming that you're doing trees of height 3 or something like that, even if you only do 5 at each split, the first split can only use 5, but it has 2 branches and each of those can use 5. So now you're talking about 15, features available. And each of those, if there's 4 children there that have splits, there's going to be another total of 20. So overall, there's 35 features used in a height 3 tree. Obviously, some of those are going to be duplicates. They have to be. But so you can see that, like, even though it seems like 5 is a relatively small number, it doesn't mean that you never, ever, ever get to use, because again, it's not 5 total for the whole tree. It's just 5 re-rolled randomly at each split. Okay. And this gives you really, really, really good variety in your trees. And that's the thing that we need is if all the trees are going to make the same mistakes, they're going to overfit. If you have one house in your um, training data that you don't know it, but it was a foreclosure, it was damaged, it's a huge, massive fixer upper, and the price is really low, you don't want that one house to completely distort um, and lower all the prices. Okay. And one way to not overfit is if you just don't let the model always see that data, you don't let the model always fixate on particular features. Okay. Um, and then Ryan mentioned something, I don't remember your exact words, but like a poison feature or whatever. You could just have this fluke where, let's say you have this one house and it has a pool, but it turns out that it doesn't just have a pool, that particular owner put like crazy expensive stuff in the house in general, right? So the pool was not your average pool. It was super nice and whatever. I don't know. It had fountains and things, and all of the appliances in the kitchen were just like super crazy expensive and da 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 da. But if you look at the data, the thing that makes it most different looking from other houses is the fact that it has a pool, right? So then this thing could easily like when the model is looking at its splits, it could very well like logically say, yes, this is really informative. This is really helping me split the data. So you can have these random correlations and all of this regularization of limiting the features, of bootstrapping the data. That's what prevents the model from being able to always latch onto the same random correlations. So sometimes it'll latch onto it. But again, the hope is that you train 500 trees in your random forest and a few of them will latch onto these perfectly accurate. This is true in the data. This correlation exists, but it's not generalizable. It's not the actual thing you want. And so hopefully we'll get really good generalization behavior. So that's random forest before we get to extra trees or feature importance. Any questions? All right. Extra trees. I think I see them. I have trouble saying like how commonly used extra trees are. But the idea is we've just been talking about we want variety, and so extra trees is a way to get even more variety. All right. To avoid overfitting even more. And so the idea here is that in a regular decision tree, if you have 25 features and you have 1,000 data points, then you look at 25,000 different combinations of splits. You look at for each, assuming they're all numeric, for each of the 25 features, you say, what if I split on the lowest value? What if I split between the first and the second lowest? What if I split between the second and the third lowest? And so on and so forth. And you check every possible split of your data. What the extra trees is saying is that when you look at that feature, the 25 features, you're going to randomly pick a split. You're not actually going to look at 1,000 different splits. You're just going to look at one, and then the one you don't even pick. It's just using a random number generator. Okay. It does mean though that um, you still will compare the 25 different random splits to see which one gives you the best split, right? So from last week, if you're looking at the Gini coefficient, you're looking for the best, purity or whatever. So so this is just like yet another thing we can do to get more variety and to regularize things more. So these techniques may at the surface seem pretty extreme, but basically what we're trying to share is that in practice, they actually work quite well. So doing stumps, doing extra trees, all of this stuff actually works pretty well. When it comes to the hyperparameters for tuning things, you have things like number of trees, height of trees, things like that. Not going to get into it too much here into the specifics, but hopefully if you understand the intuition that you want this variety in order to regularize things, that will kind of help you understand some of these hyperparameters. So generally speaking, when you're building a random forest, you don't want your trees to be very deep. Okay. Um, Again, the idea is that we're combining a bunch of weak learners. If you have really deep trees, then decision trees will usually overfit, and you're getting kind of the benefit of the voting, but that's about it. Okay. And so you really want the decision trees each to be slightly handicapped so that they have to kind of look at the broader trends and not have the ability to overfit on individual data as much. All right. So then the last thing, I already mentioned this before, feature importance is very cool. And so basically there sometimes are some options on how you calculate feature importance. But the basic idea is if you trained 500 trees to predict housing price, and every single one of those trees used square footage 3 times in various splits, and it used that way more often than any other feature got used, then that tells you that this feature is crazy important. Okay. Um, Depending on the exact settings, sometimes it's not just the number of times the feature was used, but how many data points were involved in that split. So like splitting, 10 data points for 6 is not as helpful as when you're splitting, 1,000 data points. Right. And then the other thing is earlier use, higher in the tree, closer to the root, depending on the calculation, can also be weighted a little bit more, as saying this is more useful if it was used. It's roughly equivalent to the idea of how many data points. So the closer to the root you are, there tend to be more data in there. So there's some details to the algorithm, but the idea is pretty clean, and you get pretty similar results no matter what settings you use for how to calculate importance. The idea is things that get used over and over again are highly important for making your predictions. And in theory, if something doesn't get used at all, it's a pretty good bet that you can just safely delete that feature because It's not helping at all. One question is, in between the most frequently used thing and something that's not used at all, how would you decide if something is important or not? This wasn't discussed in the chapter, but one of the things I'll add is that feature importance is all relative. So if you created a fake housing data set and you just had 25 random number generators, okay, and then you had that model trained to try to predict the price, it's going to do terribly, okay? But when you look at the feature importance, you're just going to see this chart of like the features the same way as if you had real data and a model that was actually able to predict housing really well. All right. It's all relative to the other features, not in any absolute terms. So if all the feature importances add up to 1, you can't just arbitrarily say an importance greater than 0.2 means it's a really useful feature. No, 0.2 just means it's more useful than the others, but they could all be. So one technique that people use in order to calibrate feature importance is you add some columns to your data that have random data in it, and you see where they fall in the feature importance because they should be at the very bottom. Okay. And so one of the things about trees, if I don't know how much we talked about this last week, but the more different values you have, the easier it is to find interesting splits. So if you have floating point numbers and you have 1,000 data points, there's 999 different ways you can split the information if all the values are unique. If you have gender and it's just male and female, there's only one way you can do the split. And so you can have a random correlation, but there's only one possible way to find a random correlation. Whereas with the floating point data, there's 999 different ways that you could get lucky and have a split that seems to correlate with your target variable, but doesn't actually. So when you're adding these random features, you can add a random Boolean feature that has only 2 values. You can add a random feature that has a small number of values, say, 5 numbers, right? You might have something that has 30, or you could have something that's just a floating point number between 0 and 1, and then it has roughly infinite numbers of different values. And so what you will see is that the importance of the floating point one is generally speaking always higher than the importance of the random Boolean variable, because it will get used in splits due to random correlations. All right. A huge warning sign is if you do this trick and you see that the random variables are really, really high in importance. They're near the top. They're near, all of your other features that you're hoping to use. That's a sign that you have a very weak model. Is that the predictions it was making were not terribly much better than just random chance correlations. This is something that you do on the side. You don't keep this model with the random variables for your final model, but it's something that you can do as a way of evaluating to calibrate your feature importances. Hope that makes sense. Any questions about this random number calibration?
There's a question online asking what impact does choosing random thresholds have on bias and variance?
Yeah, so did you want to or did you have another question, or did you want to kind of respond to that? Um yeah, so thank you. So the book says it has more bias. Again, I struggle with these terms. What I will say, is that it has less chance of overfitting. Okay. And usually we equate less chance of overfitting with more bias. But I don't know. I just don't find it the terminology terribly helpful. But but I'll come back to this at the end of the chapter with kind of a high level recap on bias and variance. But yes, when we talk about any one little individual thing, I tend to get a little bit tripped up, and um, so yeah, I think understanding this general notion of bias and variance as a trade-off is important, but I would like, for example, in an interview, job interview, I would never ask a question like, "Does extra trees increase bias?" Because I don't think that's a useful. Um, I think it's a hard thing and not terribly useful in practice. Yeah, Ryan, can you pass the mic behind you?
So, how do we choose the parameters for hyperparameter tuning, particularly given that it's possible that the ones we choose for tuning may turn out to be have higher feature importance because we have tuned them to the right value. So is there a correlation between how we or which ones we pick for hyperparameter tuning and which ones turn out to be important?
I'm a little confused by your question because you're talking about hyperparameter tuning and features is usually not sort of part of hyperparameter tuning.
I mean, what effect will hyperparameter tuning have on which ones turn out to be more important?
Um, so uh, so hyperparameter tuning for a random forest, and it's a similar answer for gradient boosting in the next section. Really is just about you want it powerful enough to be able to model your data, and you're fighting over fitting. Okay. These models can be a little bit slow to train because if I said train 1,000, 3,000, 5,000 models, that's obviously orders of magnitude slower than if I just said train one model in general, right? Just because you're training thousands of them. Um, so, um, so that's the main reason why you don't just choose a really large number of models. Okay. From the perspective of regularization, if you chose 1 million, I think that's generally speaking okay, but it's just going to be terribly slow. And so you're choosing to use 500 or 3,000 because that's a lot faster than doing 1 million and it gets you just as good of a model. Okay. So that's the most important hyperparameters, how many trees you're going to do, whatever. Then the other parameters are not as important. These models are fairly robust to different hyperparameter settings. And so you can do a fairly small, fairly limited amount of hyperparameter search just to say, do I get slightly better, slightly worse results if I tweak this? I would say tree height is a very important parameter. If you think your problem is very simple, go for very short trees. If you think your problem might be more complex than is typical, then you can experiment with letting the trees go a little bit deeper. And then there's some other settings, but again, usually at that point you're talking about like the last decimal place you get slightly better, slightly. It's not like you're going to get night and day a good model, bad model just because you tweaked something like min split size or something that they talk about in the chapter. Does that answer your question? All right. Yeah. Yes, this could be applied to any model. However, it has to be a model that has some type of feature importance output. And so random forest and gradient boosting are the ones that are most commonly used that have this feature. It's not so much about improving performances as understanding how well your current features are are helping your model. Okay. So in particular, tree-based models, the trees choose what feature they want to use at each split, and they can choose to completely ignore a feature. So if you had a small model, small number of features that were all really helpful, they could just never use any of your new random features you added, and they could appear at the very bottom. Okay. A linear regression doesn't really have the option to ignore features, so you have to be a little bit more careful. So there's only certain models that have the ability to choose and ignore features and then thereby give you a feature importance. But for any model that has that ability, then you can freely add these random features as a test. Again, not for your production model, because in theory, if they're all terrible features and you have really great features, they'll just be at the very bottom of your feature importance list. Thanks. All right, so let's move on to boosting. So what we see in boosting is we've now finally hit the point where we have something different. Okay, all of these other things that we've talked about up to now, it's just train a bunch of different models, and we want some variety, and the models themselves are not correlated. With boosting, what we're going to see now is the result of training the first model is going to impact how you train the second model. And the result of that is going to impact how you train the third model. So it's still a algorithm that uses many models, but this is fundamentally different. And in the end, what experience has shown is that this is more powerful than just having a bunch. Having a bunch of them kind of fights overfitting. But this has ability to actually fundamentally model more powerfully is my intuition around it. All right. So AdaBoost, the high level gist is I've talked about in some of the previous meetings about in some algorithms, certain data points are more important than others. Linear regression, every data point is equally important. Support vector classifier, in the extreme, you only use 2 data points, one from each class, and the rest of the data points are ignored. Here in AdaBoost, what you do is you train your first model, and then you look to see where its predictions stink, and you raise the importance you raise the weighting of those models. Okay. And then you train a second model, and then you combine the results of those two. And where the results of those two still stink, you increase the weight of those. And where those, get the predictions right, you lower the weight on this. And so the idea is if you have 5,000 data points and the first model, predicts 4,000 of them right, have the second model focus on just the 1,000 that it didn't do well on. And if by combining those two, it does well on 4,800, then have the next model focus on just the 200 that it didn't do well, and so on and so forth. And so in theory, if the data was modelable, then you just add a bunch of these models, and eventually you'll be able to predict everything. Okay. In reality, data is not that clean, and depending on the kind of model you have, it can just overfit easily when you keep slicing things. Okay. So you have to worry a little bit about regularization and whatnot. I could say more, but honestly, I've never used AdaBoost. I don't know, Ryan, have you ever used it?
I've used AdaBoost. There's all different forms of boosting, but gradient boosting and specifically the bottom option, the hist gradient boosting, is what I use almost all the time now, just because it's infinitely faster.
Okay. Yeah. So so that's the intuition. And again, the book has very good sort of coverage of what's in Scikit-Learn. But AdaBoost is not nearly so popular as gradient boosting. Yeah. So Cat Boost is gradient boosting. It's not AdaBoost. So Cat Boost, XG Boost, and Light GBM are all going to be the next topic, gradient boosting. Yes. All right. So let's move on to gradient boosting. Again, I'm hoping you guys have read the chapter, so I'm not going to, explain everything. But the idea here is in AdaBoost, you simply say, wow, you did a terrible job predicting these. So let's focus our energy in the next round on these things that you predicted badly. Gradient boosting does this in a numeric way instead of just in an importance way. So it's easier to talk about this in terms of regression than classification. So if you're predicting housing prices, Ada Boost would simply just say, well, let's weight this data point a little bit more because you did badly on this house. But instead, what gradient boosting says is, wow, the first model got this price to within $100, and so that's a very small value. But this other house, it was off by $100,000, and so that's the really big value that I'm trying to predict. And so, if you start layering models and you get better and better predictions, ideally, what you're going to have is a whole bunch of values that are close to zero because the predictions are really accurate, and then a few things that it's predicting badly. But now instead of saying importance wise, let's predict those, it's saying specifically, let's look at the actual value that it missed by and let's model that. And then we'll sum the predictions from the two models. All right. So there's a pretty good diagram in the book where they show sort of this parabola horseshoe shape. And as you layer in the first, the second, the third model, you can see that it gets closer and closer because the later models are just predicting what the first one got wrong. So this turns out to be just super, super powerful. Okay. So looking at the numeric value that you missed by is a lot more information than just simply saying, I'm going to bump up the weight of this thing that you missed by. So I think that's one of the key things about gradient boosting. Otherwise, it has all the features that we've talked about with random forest. Okay. You've got bootstrapping of different data sets. You've got random subsets of features being used at each split of the tree. And then you're building many trees. In gradient boosting, my experience is typically the trees, the depth of the trees is smaller than in a random forest. You can build very small trees. And again, people have done experiments where they did gradient boosting with just stumps. So trees of depth 1. And the algorithm still works, which is a little bit crazy, but it does still work. The next section is histogram-based gradient boosting. And I'm not sure, Ryan, you may have a comment on this. I don't think that necessarily the histogram-based gradient boosting is more accurate than regular gradient boosting, but it's zillions of times faster. Okay. So imagine you have a very large data set and you have 100 that, well, I don't know if it's very large, but imagine you have 100,000 samples in your data. And I have floating point numbers for a certain feature, and they're all unique. Then in order for me to decide the tree split, and if I'm looking at that feature, I have to test 100,000 different split values, or technically 99,990. I have to test approximately 100,000 different things. Okay. What the histogram thing does is it says, if I have a histogram with 200 buckets, then I'm going to collapse all those 100,000 unique values into just 200 buckets. Not only that, but my understanding, correct me if I'm wrong, is I do this once up front as a pre-processing step. I don't keep recalculating my buckets. Okay. And so basically now I only have to check 199 splits every single time I build every tree and at every split level. So large data sets, the benefit of histogram is a lot bigger than in small data sets. And so this just is like zillions of times faster.
Yeah, so the big advantage is you don't have to try all the different splits. Like typically you get just as much value out of saying split it into 512 or something like that. That's fine enough that if you're saying I have values from 0 to 1, splitting that up 512 times, you're taking tiny little cuts of the data already. Random piece of history, NVIDIA made their own like GPU implementation of gradient boosting, and it was based on this same thing. And on Kaggle, everyone was trying it out and saying, "Oh, it's so fast," but then in reality, what was happening was it was taking less bins, and people were seeing it's getting me way less accuracy, because instead of doing 512, it was 64 or something like that. And so people were seeing actual impact on their accuracy that they were getting. So that value does matter, and it is actually something that you can tune, but most of them have good enough defaults that it doesn't really matter. You might get better from actually doing the full precision thing, but typically it's like a rounding error.
Yeah, so if this is like 100 times faster to run, you can do a lot of experimentation. I suppose in theory, if you found like a really good set of settings or something, you could try then maybe doing one final run with regular instead of histogram based. I think the book mentions a very common implementation is they max you out at 256 bins, because that can get represented as an 8-bit integer. And then the algorithm is all optimized to just run on these short 1 byte integers. And so just in terms of like memory and compute and everything, everything's like hyper optimized for this scenario. So that's a common thing that you'll see, where the bins are 255 or less, something like that. Yeah. And so then also the book has a little whatever call out where they say, hey, we're talking about scikit-learn, but just so you know, there are these other libraries. XGBoost came first, and so to some people, XGBoost is sort of synonymous for gradient boosting machines, the way that like Kleenex is synonymous with tissues. So somebody may say, I trained an XGBoost model, and they don't literally mean they use that library. They might have actually used LightGBM, because that's how much whatever name recognition XGBoost got. I think the conventional wisdom today is people are really happy with LightGBM, and so in the Python universe, that's kind of the go-to. And again, going all the way back to like chapter 2 of the book, I'm not saying take your data and immediately go train it with LightGBM. I think that you should do a baseline. You should try simpler models to understand and things, but you may have an expectation that LightGBM is ultimately going to give you the best performance. All right. The tuning hyperparameters are pretty similar. And again, the idea is just that we want weak learners that won't be capable of overfitting, and we want many of them, and then in the end we'll end up with a pretty good model. So in addition to the number of trees, the number of iterations, depending on what implementation, what it's called, there's also this learning rate that comes into effect with gradient boosting. And generally speaking, you can start with all the defaults. I don't know. I'm trying to think about how I want to say. These models, these algorithms usually work quite well with all the default settings for the hyperparameters. I don't know if you want to add any color.
I think, can I share my screen for a second?
Oh yeah,
I'll show.
Yeah,
I'll show something
because there's like a zillion settings you can set, but that doesn't mean that you need to want to play with all of them.
So this is something that I like to show people just to understand the magnitude of knobs that you can tune with this. So this is the LightGBM page showing, like, they consider these core parameters, but then if you look at this, there's so many different things that you can tune. And so one of the like rabbit holes that I've seen people go down is they say, oh, I learned this hyperparameter tuning trick. I learned Optuna. I learned some library that's supposed to go try all these out. And I just throw compute at it and I try a whole bunch of things. But I would honestly say ignore most of this. Like out of the box, you're going to get decent performance. And then if you want to try to tweak more, I would say focus on the stuff that we actually talked about today. So like look at max depth, look at bagging fraction, look at feature fraction. Those would be the three that I focus on if I were to try and tune anything. The rest of these have an impact, but you can get totally lost in all of the options that are here.
Yeah, and you can Google. There are articles where people say like, "What are the most important?" and they'll get you down to a list of usually around 8 or so. And I would say you don't necessarily even need to look at all 8 of those, but if it's not in the articles, you really, really probably, unless you're an expert and have some strong reason, you don't need to mess around with those hyperparameters. Um, I see I missed a question. So from feature importance, can we know certain features are highly correlated? Um, so um, so first to answer the question, no, I don't think that feature importance tells you anything about if features are correlated. And one of the things I will say is that the idea of correlated features is really important for some algorithms. So for linear regression, features that are highly linearly correlated cause problems for linear regression. Okay. You can have instability. So if I think the example I might have given a number of weeks ago was if you had the person's age in years and you had the person's age in months, they're basically the same thing, but there'll be some slight differences. Having both of those in there uh, can cause some numeric instability, like some floating point rounding errors. If at some point it's sort of like taking the difference between these two and it's a really small number, and then it does the reciprocal of it, basically kind of a thing. If your goal is to have a highly accurate model, random forest and gradient boosting trees will give you very accurate models. If you had person's age in years and person's age in months, it might at different points do tree splits on one or the other of those. And the reality is you could have gotten rid of one or you could have gotten rid of the other, and you would have gotten a very, similarly good model. But it doesn't break anything by the virtue that you have correlated features and the tree decided to sometimes use one and sometimes use the other. So there's two things you need to decide whether you care about. So one is, does the algorithm care about correlated features? And most algorithms other than linear regression don't care about correlated features. Okay. The next thing you might care about though is you want to explain your model. So when it comes to model interpretability, then it can be a problem because you might find that age in years and age in months both look a little bit lower on your feature importance list because they've basically split the weight. So if they normally would have gotten a 0.3, they might both show up at 0.15 and it'll look like they're less important. But in fact, it's sort of representing the same concept. So we're not going to get too heavy into the interpretability, but I will mention that another thing now that people use is SHAP values, SHAP, and again, you still have an issue in terms of correlated features, but it turns out that SHAP values have some very nice properties, but they can be very expensive to calculate because you do subsets of your data. And so if you have like 1,000 data points, there's like 2 to the 1,000 different subsets you can have. And if you have even more data, then it's an even larger thing. But it turns out that there's a very efficient way to calculate SHAP values for tree-based models. And so all of the gradient boosting, the popular libraries, these days they support SHAP values, and that's a way to again, we're not going to go way down into interpretability, but that's a way in which you can get additional information. Do you want to add something?
Yeah, I'll share my screen again. So one thing about the feature importance is I think sometimes people read a little bit too much into it. So you can the feature importance is trying to be some proxy of how important is this feature, how critical is it for the thing that I'm predicting. So I pulled up this Kaggle notebook. It's kind of just a random one, so don't read too much into this. But there's multiple different methods for determining importance. So people have come up with all different strategies of how do I look at these trees? How do I look at my random forest? How do I pull information and derive insight out of what has been constructed out of my model automatically? And so there's two kind of common methods. One of them is based on splits. So you can say basically how often was this feature used in my tree? So just like how many times was it used as a splitting point for all these different things? So this one, I guess they're looking at diamonds or something. I don't know, but it's saying basically, look, clarity is used in 700 of my trees. That's roughly how I would read this. And so clarity is used a whole bunch, so it must be important. But then if you look on the other end at gain, so gain is another way of looking at this, basically saying how much like extra accuracy did I get every time I use this model? And you can see that all of a sudden clarity is like maybe in the bottom three features. So that's one of those things where sometimes you get a nice sort out of things and you say, oh, this is the feature that I really thought was going to be predictive and it's my top feature. So I trust this interpretation of things. But other times you can say, use both of these methods and get totally different outcomes. And then you have to kind of go, okay, maybe I don't read too much into this. Just one thing I wanted to highlight on the feature importance.
Thanks. That's really good color. All right, let me share my screen and see if I can wrap up here. Um, okay, the last topic in the chapter is stacking. I'm not going to say too much about it. The first time I heard of stacking, I thought, oh, this is really cool. You know, you train a bunch of models and they're smart. And now I'm going to train the super intelligent model that then gets to build on top of all the smarts of these other models. And the reality is, good algorithms tend to pretty much exhaust all of the information that's in your training set. So there really isn't any super intelligence to be gained by having another model stacked on top of it. Um, Even in Kaggle, where you see people will go to enormous lengths uh, in order to get an extra 0.001 on their score, you see people will do voting type things and average, you know, soft voting, hard voting all the time. Okay. Probably there's not a single gold medal winner that doesn't do some kind of multiple model averaging voting. I don't even know. I don't know if I've even seen stacking in the last few competitions used even once. Okay. You know, it can come up, but again, so I would say sounds pretty cool, but in practice, not really um, not used very often. And then in the business world, it's just like voting. You don't really see because again of the extra time training and the extra complexity. Stacking is yet another level of complexity way beyond that. And so I'm sure somebody can show a counterexample, but like for regular old common business uses, like just predict customer churn, I've never seen a stacked model used in practice. So not going to say too much more about that. All right. A couple notes and then some questions that I wanted to just kind of get to recap things. Um, so tree models don't require scaling, and some implementations allow null values. And I think nulls are very easy for the histogram models to use because they just allocate one bucket for nulls and then all the other buckets for actual numeric values. So this again, in addition to how powerful they are, makes gradient boosting algorithms really convenient. It's like, wow, I don't need to scale my data. I don't need to clean the nulls. You still should do your EDA and clean if you have bad values, right? So if you have inaccurate readings on your thermometer from one thing, that's going to screw everything up, because if it was actually 70 degrees and it says it's 90 degrees all the time, you might need to throw away data from that particular sensor. So you still need to do your homework, but there's not a lot of data prep required in terms of collinearity, scaling, nulls, any of those kinds of things. So that's pretty great. There are variants on these algorithms because they're so powerful. So in 2 more chapters, when we talk about anomaly detection, we're going to see a variation on random forest called the isolation forest. Okay. Another thing that has come up, sometimes people ask me about, they say they really, really want something interpretable, like not just importance, but like interpreting why did the model predict this or that. And so I'll mention, I've seen in the literature multiple times, there's a monotonic constraint option in the big libraries. I don't know if Scikit-Learn has it, but definitely like LightGBM, XGBoost. And this forces the splits to sort of always be ordered left-right in the same direction. And this makes the models much more interpretable, because instead of like just this crazy nested if then else thing, you can kind of just sort of summarize the tree by saying at the end of the day you have this section on the left and then these sections in the middle and this section on the right. So it makes it more interpretable. So that's an option if that's something you guys are interested in, to do a little more reading. In the exercises, so 1 through 7 recap understanding of this chapter, and the last 2 let you practice some coding. So those are good exercises. I took a look at those. I wanted to highlight exercise 3 asks, of all the things talked about here, which ones are parallelizable, where you could train different models. If you had multiple computers, you could train different models on different computers. Okay. And I think that's an important thing to understand. So fundamentally, the boosting algorithms are not parallelizable, because you have to train the first model and then see where it does well or poorly, or look at the residuals for gradient boosting. And then you can train the second one. And you can't train the third one until you know the residuals from the first 2, and so on and so forth. So that is a big downside in terms of how long you have to wait for these things to train. But I would argue that's at the core of what makes them more powerful than the other algorithms. All right. So then I have 2 questions that I came up with. The first question is, random forest and gradient boosting are 2 of the most powerful algorithms, and they use decision trees as their building blocks. Why are we seeing trees getting used more often than other things as building blocks? Why not linear regressors or support vector machines or other things? Why do we see trees used as a building block? Anybody have thoughts about this? So one possibility is quicker. I think quick is part of the answer, okay, but it's not the whole answer. There is a more theoretical thing, and my hint
Could
is that this goes back to like bias and variance. Yes, please.
could it be because of the feature selection and which result, I might not be getting it fully correct, the Gini impurity value which it assigns for every node, because of which it helps in reducing the bias and variance, and that's when the decision tree at each node, when it is selecting the feature, it'll have the important feature selected. Probably that's because, I mean, that's the reason decision trees are powerful.
Yeah, I think that gets at what I'm looking for. I'm going to say it in a little more general way. Okay. So again, I get tripped up. Maybe it's just me. Maybe I just have trouble getting my arms around. But when we talk about bias and variance in the nitty-gritty details, I get tripped up. I get confused. Okay. But at the end of the day, you have this bias variance trade-off where something like linear regression has a high bias in the sense that it has a strong view of the world. That's like sort of one intuition, right? It's highly unlikely to overfit is another way you can say it. But geometrically, you can just think that it has a very limited ability to fit data. It can only fit things that are linear. It can't fit anything that's curved. Okay. And the nice thing, though, about something that's high bias is that it's low variance. Okay. Which means that if you change the data a little bit, it has a tendency to give you a very similar model. All right. It's a lot more predictable. Trees, on the other hand, okay, are low bias. They can fit any shape of data. It really does not matter because the way that they do splits, they'll work around any shape, any curve. It doesn't even have to be like not only curved, but it could just be like a forked thing. It could be discontiguous where you have like a circle here and a circle there, and they're not even connected. And the trees just they absolutely don't care. So they're super, super low bias. But the problem is that they're very high variance. That if you tweak the data a little bit, you could get a very, very different tree. What we want is a model that's low bias and low variance. We want a model that's predictable, generalizable, but doesn't require assumptions about what the data looks like, such as being linear. So when we do ensembles, what we want to do is we want to take a model that's high bias, like linear regression, and figure a way to lower the bias. That is not easy. It's linear. How do you lower that bias? Okay. Or we take a model that's high variance and we lower the variance. People were like, I know how to do that. So if you look at the chapter, you start by just doing voting. So I just build 5 of them and I have them vote and I've lowered my variance a little bit. Now I'm less prone to overfitting. Okay. And then I come up with smarter things. I can do data bootstrapping. I can do bagging. And then I can ultimately do this boosting thing and I can look at where the first model was weak and I can build upon that and blah, 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 blah. And so that's one of the core reasons why trees are used is because it's a lot easier for us to figure out how to lower the variance than it is for us to figure out how to lower the bias. I'll give you a counter example. Okay. So there's an algorithm called MARS, multivariate adaptive regression splines. And basically, what that does is it builds on linear regression. But what it allows you to do is to piecewise chop up your data into subsets. Okay. And so the if you look at the diagram, you see the word not. So the word not describes the point where you split your data into halves. Okay. So the idea is here, if you have some data that looks like a sine curve and you tried to model it with linear regression, it's just going to fail completely. All right. If I split it into 2 parts with 1 knot, if I split it into 3 parts with 2 knots, it's actually okay. It's not really great. And then you can see 3 knots, 4 knots. All right. And so something that's piecewise linear can fit, you can lower your bias with a model that's already low variance. Mars, I don't know. I always thought Mars was kind of a cool model. I don't know if it's used that much in industry. The really cool thing about the Mars algorithm is that you would think that if you did this, you might overfit terribly with and that's only true though if you have a gazillion knots. So if you have a relatively small number of knots. The other thing that's really cool about the Mars algorithm is it's actually really fast. So you might think like, gosh, I have all these different features in all these different places where I could put a knot. In a decision tree where you're classifying, you're just saying like, well, is it dogs or cats if I split this way? If I'm predicting the impact of putting a knot in some place, then I have to actually train a full linear regression on each left and right half and decide if that knot helps me and blah, blah, blah. But amazingly enough, the developers of this algorithm figured out a way to do it, and it's super duper fast. So this is for your mental model, like a way in which you can build on something that's high bias instead of building on something that's high variance. Okay. I will present to you. I was going to look it up. I didn't get around to it, but the original neural networks, so just simple, fully connected networks using ReLU as your activation function, those can only output piecewise linear outputs. So it's a lot like Mars. It just is going to have straight chunks that are split based on wherever your ReLU cut points are on your different nodes, your different layers. So ultimately, I would argue the original neural networks are a form of taking a linear model, because each node, each perceptron is just doing a matrix multiply. It's just a linear function. Okay. It's a way of taking a linear model that's high bias, low variance, and turning it into a low bias, low variance result. So in the end, we always want the same thing. We want low of everything. So if that, I hope that helps your intuition in terms of gradient boosting is taking something high variance and how do we combine many of them to make it better. And there are actually approaches. It's not the only way, but so hopefully at a high level that makes sense to me in terms of bias versus variance. I just get tripped up when you get into the nitty gritty details and you say extra trees, is that higher or lower variance than regular trees? And it's like, but hopefully at the big picture level this makes sense. Any questions? Yeah, can you?
How does it determine the splitting point for the piecewise linear regression for this particular multi-adaptive linear regression model?
My understanding is Mars does actually try all the possible splits. So if you had 1,000 data points, it's trying like 999 different splits, but somehow it does it in a way that's efficient. So that, and again, like a tree, it's trying 999 splits as well, but it's just in this case, it's doing linear regression on each split. And that seemed like that would be more expensive, but there's some cleverness where they're not fully doing the linear regression from scratch on each possible split. So that Mars, it's a lot slow. It's slower than linear regression, don't get me wrong. But for what it's doing, which is really quite cool, it's actually reasonably fast. All right, there was one chat question earlier that I know I didn't get to. Okay, it doesn't look like it was a question. Any other final questions before we wrap up for today? All right.
One
Awesome.
last
Thanks, guys.
question.
Oh, yeah.
The hands-on machine learning with R, do you have a reference for that?
I can post that in Slack. Yeah, I think I read this book a long time ago,
Okay.
but I just did a Google search because I was looking for a pretty picture for the Mars, and I wasn't finding. And so this was the first place where I found a nice picture that shows as you add more knots, your piecewise linear thing gets closer to your curvy shape.
Is this an older book?
It is. It's my understanding is this is quite old.
Okay, thanks. That might be the reason I'm having troubles with it.
Yeah. All right, thanks. So next chapter of the book is in 2 weeks because next week we have our monthly event. So again, vibe coding a chatbot application from scratch, computer vision, training CNNs, and latest ML news of the month, latest models, things like that. But before that, in 6 days, Friday evening, social. Hope you guys come to Mission Value and hang out with us. Yeah. Yes, yes, all the meetings are recorded. It'll be a different playlist, but it'll also be recorded. All right. Thanks, everyone.